Welcome to this video on logarithms. So this is a basic introduction to logarithms and how they relate to exponential functions. And the first thing you'll notice that I wrote up here is a conversion between exponents and logs. And so this is really the fundamental thing of logarithms, is that logs are basically just the inverse of exponents or exponential functions. And so the way that I rewrite an exponential function is to do it with a log. And so these are sort of the same as like with squares and square roots. They undo each other. Same thing with this. Exponents or powers and logs undo each other. And so we'll go ahead and look at that a little more carefully here. The first thing I want to try is just converting back and forth between a couple of things. So if I have, let's say, one that we already know, so let's say 8 equals 2 to the third. So that's a true statement that I know. It's an exponential form. I got 2 to the third, and I know that equals to 8. Well, what I'd like to do is rewrite this in a log form where I can get this exponent 3 out of the exponent. So to convert that to a log form, what I would do is just take the log base 2. Alright, so it's still the same base as the exponential base right there. So log base 2 of what's on the other side, the 8. Right, so of the 8 equals this exponent. And so that equals this. And so with this, our whole goal here is to get that 3 out from inside this exponent and by itself in this type of equation. Much like if I have an x squared, I'm trying to get a square root to get me what's inside that square and undo it. And so logs basically behave the same way. Alright, so with something like this, a key part here is the base. This exponent has a base b. Likewise, I call the base b on the log my base. What's inside is the argument, and it helps me to think of the logs always equal to the exponent. So if I have an exponential form, the logs always equal the exponent, and then whatever's on the other side goes inside that log. So you'll get something like this. Now this will give us a way to solve certain equations later on. So if I want to convert, say, something like, let's say 2 to the x equals 5, right, something like that. One way that people try to do these is to try to get these to be the same base and equate those. Well, with a 5 I can't really do that, so there's no way to really write 5 as a nice power of 2. And so what we'll do is just convert this to logs, and we'll talk about this a little bit later on. But right now, just strictly converting to a log, this will be the same thing as a log base 2. Right, so I do the same thing, log base 2 of what's on the other side, the 5. Alright, so I'll put in the 5 equals that exponent, so equals that x. Alright, and then if I can compute that log, then I can go ahead and find that x. And so that gives us one way to solve sort of these basic exponential equations right here, is just to convert them to this log form and then evaluate that log. Alright, so we'll talk about that log in just a second. Alright, one thing that I do want to put up is some log properties that are going to be handy for us coming up here pretty soon. So a few log properties that we'll need and how they relate to the exponential form. So I'll go ahead and just put those up right here. Alright, so here's a few log properties that I'm going to talk about. These you should definitely know when you come across them, but I won't say, list out these log properties. I won't ask something like that, but you should be able to use them in a problem. So we'll go ahead and do that here in a second. The first one here is log base b of 1 is always 0. So the log base b of 1 inside that log is always going to equal 0. The reason for that is that if I convert this to exponential form, that means this b to the 0 is just going to equal the 1. So there's the exponential form, b to the 0 equals 1. So these are equivalent statements right here. And just like we know b to the 0 is always 1, we should know log base b of 1 is always going to equal 0. So, and that's a property I'm going to use when I look at the graphs as well. Also, log base b of b is always equal to 1. may not be obvious in log form, but if I change that to exponential form, this b raised to that power of 1 is going to be the b inside the log. So we just get this b to the 1 equals b. And in exponential form, that definitely makes sense. So again, these are equivalent statements, just different forms, exponential form and log form. Here's the next one. Log base b of b to the x is x. All right, this is one that does get used quite a bit. And the reason for that is that if these bases match it, I just get that exponent that's up here. So again, converting to exponential form, this b in the base to the other side, x, equals what's inside that log, that b to the x. So this base b to the x on the other side equals that b to the x. And in exponential form, again, that makes sense. b to the x should be the same as itself. All right, the next one is actually on this right-hand side right here. B to the log base b of x equals x. And this is in exponential form. So base b raised to a log power will just equal what's inside that log as long as the bases match. And so, again, this comes from going back to a log form. So a log of that base b of what's on the other side, x, equals that exponent, log base b of x. So this turns out to be just log base b of x is log base b of x, and that should be a true statement. So this shows you that exponentials and logs are inverses of each other. If I put an exponential inside a log, I just get the exponent. If I put a log inside an exponential, I just get what was in the log. So as long as the bases match, that'll always be the case. And we'll go ahead and do a couple of problems here next. Alright, so here's a problem I want to solve. This log base 2 of 1/2 equals x. And sometimes you'll see it without parentheses like this. Sometimes you'll see it with parentheses, such as this. Really, logs are functions, so most of the time it's appropriate to think of this inside parentheses right here. But a lot of times I'll just leave it out to make it look cleaner. But we'll go ahead and put it in like this for right now. So if I want to solve for x, this log base 2 of 1/2, there's a couple of ways I can do it. And one way is just to change this 1/2, which is 1 over 2 to the first, to just a power of 2. So if I just rewrite this as log base 2 of 2 to the negative 1, all right, so remember 1/2 I can think of as 2 to the negative 1. Then I can use that log property. So the log base b of b to the x is always x. So log base 2 of 2 to the negative 1 should just be this negative 1 right there. All right, so that turns out just to be the negative 1. So that's from that third property in that list that we wrote. All right, so anytime I'm looking at that, that's the type of thing that I'll see. All right, so if we want to go back and look at that list, let's go ahead and take a look. So there it is right there. This log base b of b to the x is always x. So that's what I'm using right there with my bases as 2 for that point. All right, so that's what we get for that point. So that's one way to do it. Another way to do it on these is to use the change of base formula. And I like to put this in as soon as possible. So we'll go ahead and mention it right now. So this is the change of base formula. And this is useful for all kinds of stuff. Not only evaluating logs, but also graphing on a lot of calculators requires you to use this change of base formula, including the TI-84. So we'll go ahead and look at that. All right, so this is going to be change of base. All right. So one thing I should mention before we put this in is the standard bases that you'll see on a calculator. So if I see this just log of x, something like that, just log x with no base written, this is assumed to equal a base 10. All right, so I assume there's going to be a log base 10 of x right there if I don't see a base. Likewise, if I have this guy, natural log of x, something like that, this is assumed to have a base of e. All right, so this is the same as saying this natural log with base e of x. All right, so oftentimes I'm not going to write it with the natural log because I know that's a base e, so we don't need to write it if we already know that. Same thing with what's called the common log. This log would have a base 10, but if we know it's going to be base 10, we don't necessarily need to write it in there. So, and these two are buttons that I do have on a calculator to be able to use this log x and this natural log of x. The e, in case you're wondering, is just a constant, somewhat like pi. It repeats or it has a decimal that does not repeat as you go on. So it starts out with 2.718281828, and then it has other numbers besides 18 and 28, but it just keeps going. You can put that in your calculator if you want to see what that number is, but much like pi is 3.14, so on and so forth, this e is going to be 2.718, so on and so forth, but most of the time we'll just keep it as e. Alright, and in case you're wondering why in the world use that e, it has a lot of special calculus properties, but those we're not going to get into here. Alright, so change of base formula, let's see what that is. So if I want this log of base 2 of, let's say, 1/4 this time. Let's go ahead and do the 1/2. We'll do the 1/2. Alright. I don't have that on a calculator, but what I can do is rewrite this as the log of 1/2 over the log of 2. Alright, so I can do that right there. Log 1/2 over log 2. And with that guy, what that allows us to do is to type that into our calculator and actually calculate that out. So the change of base formula, let me go ahead and write it. So log base b of a, I can always write as this log of b over the log of a. Or sorry, let me go and rewrite that a second. Alright, so this is log base b of a is log a over log b. Or if you like natural log instead, you can use natural log of b, or natural log of a, over this natural log of b. So most of the time I'll use log, but if you really like natural log, you can also use natural log right there. Really any log of any base you can use on top and bottom, but we use these because we have those on the calculator. So let's go and take a look at a calculator and see what that looks like. So if I go ahead and put this in, right here, let's see, log base 2 of 1/2. If I wanted that, I put in log 1/2 over log 2. So the log button is just right here by the 7. Alright, so we'll go ahead and put in the log of 1/2, and then divided by this log of 2. Alright, make sure you do close off your logs when you type those in. Otherwise you are getting a division inside where you didn't intend. So hit enter, and that gives us the -1. So just like we saw before when we were trying to solve that out, that was the -1 right there. So that's another way to solve these out using that change of base formula. Alright. This will also be useful when graphing using that change of base formula right there. Alright, so let's go ahead and look at another one here real quick. Alright, so with this one right here, what I want to do is evaluate this log of base 16 of 1/4. So I want to evaluate that. One way sometimes people do it is to set it equal to x, change it to exponential form, and then try to get like bases and equate it that way. That's kind of the long way around if you know this change of base formula. So we'll go ahead and just use the change of base formula. So what this is going to equal is this log of 1/4. Alright, so I got log of 1/4 divided by the log of 16. Alright, so over log 16. And again, with this one, what we want to do is just type that in. So if I go to the calculator here, we can just type that in. So this is going to be the log of 1/4, and then divided by 16, or log 16. So let me go back. Log 16. Alright. And then that's it. Alright, so there's -1/2 for that one. Alright, so this one equals -1/2. Alright, so when we put that in, that's what we'll expect. So this one we could actually do pretty quick just by using that change right there of the inside of the log, if we can get a like base right there. This one, it would be a little bit harder to get this 4 as a base of 16, or this 1/4 right there. So change of base is definitely going to be quicker on this one. Alright, so that's it as far as that goes. Next time we'll take a look at some graphing and how this change of base comes into play. So hope you enjoyed it. Let me know if you got any questions.